Welcome everyone to my channel. I'll start covering different topics of General Chemistry 101, which will pretty much be useful for any Gen Chem classes you are taking across the world, especially United States. Let me introduce myself. I am Mohammad Sohail Rana, PhD candidate at the University of Kentucky, USA. So I'll start with the topic the valence shell electron pair repulsion theory. So that's under the molecular geometry and chemical bonding theory chapter. The reference I'm using here is General Chemistry 9th edition by Ebbing and Gammon. That's the book I liked most when I studied myself, and also so I'm choosing it to teach because I found it's really useful. But you could follow any standard book for general chemistry. It should be useful whether you choose this book or any other book. But I highly recommend to have a book because at the end of my lecture, I'll suggest you to do some exercises on your own. And if you can find it in online resource, that's fine. Any general chemistry book which you can borrow or collect, that will be the most useful thing to do. So let's begin. The valence shell electron pair repulsion or VSEPR theory is being developed to explain the molecular geometry. Now, what is molecular geometry? That's the general shape of a molecule as determined by the relative positions of the atomic nuclei. Let's look into these two examples, where on the left we have the boron trifluoride and on the right we have a phosphorus trifluoride. Although they have same number of atoms surrounding the central atom, still the shape differs. How do you explain that? Well, that's where it comes the VSEPR theory. So as we move on towards the more depth into this topic, we'll understand and learn how to figure out the shape and the geometry of any given molecule which you will encounter in your test or in the assignments you get from your instructors. So the valence shell electron pair repulsion model predicts the shapes of molecules and ions by assuming that the valence shell electron pairs are arranged about each atom so that electron pairs are kept as far away from one another as possible, thus minimizing electron pair repulsions. Here's some of the examples which you can use to figure out what type of geometry would fall for a particular given compound. Let's say there's a number of pairs of electron is 2 into the bonding pair, then you're most likely to have a linear arrangement where the most two electron pairs are apart from each other by 180-degree angle. Then if you have 3, that's going to be trigonal planar because these 3 pairs will try to stay equally distanced from each other, and that's going to be 120-degree because the total angle is 360-degree. If you have 3 and you divide them by 3, you are getting a 120-degree arrangement. Now, if you have 4, that's going to give a tetrahedral arrangement where each of the bonding pair will be located at each corner of the tetrahedral, where the bond angle will be 109.5 degree. Now, if you have 5, it becomes a little bit tricky, but here's something interesting. If you have 5, that's going to become trigonal bipyramidal. So we'll have a trigonal planar where you have 3 bond pairs apart from each other by 120 degree compared to the central atom, and then you will have a linear bond going through the center of the trigonal planar where these 2 lone pairs are apart from each other by 180 degree, but they are 90 degree from the trigonal planar. So here you have 90 degree bond angle and 120 degree bond angle, and that's one good example. How can you have 2 different types of bond angle in one molecule? Now, if you have 6 pair of bonding electrons, then it's going to be octahedral. They will be at each corner of the regular octagon, giving a 90-degree bond angle. Now, let's look into the balloon model to visualize it more accurately with some real examples. So for the linear, as you have 2 bonding pair, take 2 balloons and connect them, and you'll get the linear geometry. example is carbon dioxide, CO2 molecule. Now, for trigonal, as you have 3 pair of electrons, take 3 balloons and connect them, you'll get the trigonal planar. The example is sulfur trioxide. If you have 4, take 4 balloons and connect them, and you'll get the tetrahedral, regular tetrahedral shape, and that applies for methane, CH4. Now, for trigonal planar, as you remember, we have 2 different types of bonds there. So you take 2 different types of, not 2 different type, 2 different color balloon. So for trigonal planar, take the blue, and for the linear, take the green, and connect them. You'll form the trigonal bipyramidal shape, and from there you can easily locate which one is 90° and which one is 120°. And for octahedral, as the bond angle is only one type, which is 90°, you just take 8 balloon and connect them, and you'll find you'll get the shape for the sulfur hexafluoride regular octahedral shape. So what we are seeing from here is the direction in a space of the bonding pairs gives you the molecular geometry. Now, how do we figure out shapes for central atom with 2, 3, or 4 valence electron pairs? Let's say 2 electron pairs we learned already, that's linear arrangement. For 3, it's trigonal planar arrangement. For 4, it's tetrahedral arrangement, but the actual shape will differ based on how many bonding pair and how many lone pairs you have. So let's consider methane. It has 4 bonding pair, and all of them are used to make 4 bonds with for 4 carbon hydrogen bond. So it's the regular tetrahedral shape. Now for methane, although it has 4 pair of electrons, but only 3 pair is for bonding and 1 is left for lone pair. So we are having trigonal pyramidal shape. And for water, we have 2 lone pair and 2 bond pair. So the shape is becoming bent, although it has 4 electron pairs, because we don't have bonds for all pairs. Now, how do you do the prediction of geometry by a VSEPR model? So start with writing the electron dot formula for the molecular formula. For example, beryllium chloride, it's in group 2, so it will contribute 2 electron to the bonding with 2 chlorine atom, and those 2 chlorine atoms have 7 bonding electron for each, so you'll have 7 plus 2, it's going to be 16 total electron. So you distribute them following the octet rule for chlorine, and it's going to be and 2 electron rule for the beryllium, because it can have only 2, not 8 for the ones which are higher in atomic numbers than beryllium. So you can see you have 2 bonding pairs on 2 sides of the beryllium. That gives you a linear arrangement. Now, you may not always encounter the simplest one which I showed, but you will be encountered with more complex one, like you may have 3 electron pairs, and all of that could be bonding pairs. You're lucky at that time. You have a regular trigonal planar shape like boron trifluoride. Now, if one of them is lone pair, then you get a band shape like sulfur dioxide. Next group is if you have 4 pair, which I showed in previous example as methane, ammonia, and water. So if you have if you have no lone pair electron, it's regular tetrahedral. But if you have 1 pair, it's the trigonal pyramidal shape. And if you have 2 pairs, it's the band shape. Now, the bond angles, you already noticed that the bond angles are not always standard, as you start with the total number of electron pairs. So if you have 4, it should be a standard tetrahedral shape, but that's not always, because you don't have the bonds for all the bonding pairs you have electrons. Some could be lone pair. So based on that, your shape will differ. Like for methane, it's standard tetrahedral 109.5°, but if you change one of the hydrogen by chlorine, it expands a little bit more, because since chlorine is a bigger atom, its bond length is more bigger, its bond is longer than the other three bonds, so those three can stress a little bit but more. Now for ammonia, it's opposite, since it has one lone pair that will squeeze other three bonds, and it will be reduced to 107 degree. Now for water, it has two lone pair, so the bond between oxygen and hydrogen will get squeezed more. That's 105. So you can see that the number of lone pairs impacts the bonding angle, and also what type of bond you have, that can also have an impact on the bonding. Now, if you have central atom with 5 valence shell electrons, there's 4 scenario. One is no lone pair. That in that case, you have a standard trigonal bipyramidal shape. If you have one bond pair, that's going to be seesaw or distorted tetrahedron, like for sulfur tetrafluoride. If you have two lone pair, it's going to be a T shape. The two bond of the trigonal plane will have lone pairs, and others three will carry the bond pairs. So in that case, it becomes the T shape. And then if you have three lone pair, it becomes a linear shape, although it has total 5 electron pairs. And that's the example for xenon difluoride. Now, with central atom for 6 valence shell electron pairs is going to be 3 scenario. 0 lone pair, it's the regular octahedron shape like sulfur hexafluoride. 1 lone pair, you'll have a square pyramidal shape. 2 lone pair, you'll have the square planar shape. So here's some of the examples I have from exercise from the book. This book is really nice book. It has different levels of exercises, like it has some concept explorations, which is pretty standard for everyone, and it gives you some conceptual problems, which is more advanced, and then it gives you some practice problems, general problems, and strategy problems. Those are more advanced, and then cumulative skill problems. So if you start with the concept explorations, and then conceptual problems, and then practice problems, then general, and then strategy problems, you'll be able to solve the cumulative skills problems. Those are the highest complicated problems. So I highly encourage you to go throughout the exercise of this book, or the book you're going to follow, or the resources you're going to follow, and I hope you'll be able to learn that VSEPR model and apply it in your exercise, in your assignments, in your exams, and or for your self-learning. Thank you very much for being with me.